In this section, we are going to talk about triple integrals in cylindrical and in spherical coordinates. Now, when we talked about double integrals, we learned that we can integrate them over rectangular coordinates. It's kind of the usual thing we do. But we also saw that in certain circumstances, it is useful to integrate a double integral over polar coordinates. In this section, we're doing the same thing with triple integrals. We're going to see that in some situations, rather than integrating a triple integral in rectangular coordinates, it might be much easier to integrate it in cylindrical or in spherical coordinates. All right, so let's start with cylindrical coordinates. So say I have some triple integral over some volume E. We're integrating it in with respect to our rectangular coordinates x, y, z. So I can do a change of variables and instead integrate it over cylindrical coordinates. And often, depending on the nature of the volume or the function that we're integrating, it might make things a lot easier to integrate in cylindrical coordinates than in rectangular coordinates. Okay, so we're going to integrate with respect to variables r, theta, and z. Okay, now when integrating with respect to cylindrical coordinates, we almost always integrate first with respect to variable z. Okay, theoretically you don't have to, but pretty much every example that you're going to see in this class, that you're going to integrate with respect to z first. It's going to make things easiest. Okay, and then we could integrate with respect to r and theta. Now we know that when we integrated a double integral with respect to polar coordinates, we had to add in an extra r to account for the change in variables. We're going to have a similar thing here. In fact, it's going to be the exact same thing here, because once we finish that first integral with respect to z, what are we left with? Okay, the outer two integrals are respect to r d theta. The outer two integrals are with respect to our polar variables. So all I'm doing in changing from changing a triple integral from rectangular variables to cylindrical variables is I'm changing the x and y to the polar variable system. Okay, those last two integrals to the polar variables. And so that change, since it's just those two integrals, it has the exact same effect. I'm going to need to throw in an extra factor of r to account for the change of variables. So whenever you use cylindrical coordinates, you need to throw in that extra r. So let's take a look at this first example here. We want to evaluate the triple integral of e to the z over region E, where the volume E here is enclosed by the paraboloid z equals 1 plus x squared plus y squared, and it's within the cylinder x squared plus y squared equals 5. Okay, so before we do anything else, let's sketch our volume. Give myself enough room for this. Okay, so x, y, z. So our paraboloid, it's just our standard paraboloid, but it's shifted up 1 unit. Okay, so let's say that's 1 unit up. So it's something like this. Okay, so that's our paraboloid z equals 1 plus x squared plus y squared. And we're also within the cylinder x squared plus y squared equals 5. Okay, so x squared plus y squared equals 5. That is a circle of radius that is equal to the square root of 5. Square root of 5 is just going to be a little bit bigger than 2. Okay, so 1, 2. Probably will need to extend my paraboloid up a little bit to meet the edges here. Okay, and so that's the circle in the xy plane, and then it goes up. And then also we're bounded by the xy planes, right? So we don't go below that plane. Okay, so hopefully you can kind of see what's going on here. The paraboloid and the cylinder aren't meeting up very well in my picture. Hopefully you get the idea. Let me draw it again. A little nicer now that we have an idea of what we're dealing with. I often draw two pictures when sketching out the volume for these three-dimensional shapes, because I'm graphing these different surfaces, and sometimes what I get here isn't a helps me understand what's going on, but it's not a great visual representation. Okay, so we have our cylinder, a little smaller this time. And then our paraboloid. Actually, let me make that dotted because it's on the interior. Okay, so it's kind of like a little cup. All right. In case you're having a hard time visualizing it, here it is in Desmos. Okay, I don't know if you could see, but the interior there, let me change the color. The interior there is hollow. That's the inside of the paraboloid, and then the outside is the cylinder. Okay? All right. Now looking at this, just looking at it, this is mostly a cylinder, right? We have this weird shape here. We have a little divot cut out of the cylinder, but it's mostly a cylinder. So it makes sense that maybe we should be using cylindrical coordinates here. Okay? All right. We're going to use cylindrical coordinates. Set up our triple integral. We need to make sure if we're going to use cylindrical coordinates, we rewrite our function in terms of our cylindrical variables. So just as a reminder, maybe I'll do it down here. Just as a reminder, x equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared. Tangent of theta equals y over x, and z equals z. That's our relationship between our rectangular and our cylindrical variables. Okay, so when you are changing a function from rectangular to cylindrical, you got to use those properties to make the changes. Okay, in this case, it's very straightforward. It's just e to the z. So the only variable I need to change is z. And in cylindrical variables, the z in rectangular is equal to the z in cylindrical. So it's actually going to stay exactly the same. Okay? But because I'm making the change to cylindrical variables, I also need to include an extra factor of r. Don't forget that factor of r. And I will integrate first with respect to z, then with respect to r, and then with respect to theta. This is generally the order you want to go in when integrating with respect to cylindrical variables. Okay? All right. So let's integrate first with respect to z. We're going to do this the usual way. Okay? That first integral, it's the same z we use for rectangular variables. So we're going to think about it the same way. So imagine you have a strand being cut out through this volume. So in through the bottom here, the xy plane, and out through the top, which is the edge of the paraboloid, right? No matter where I put this, that's going to be what happens. Oops. Okay. So it's just the same as we have been doing. So we just want to go for each one of these little strands here, one of these strands, lowest point to highest point. Okay. So for each strand, it enters in through this surface, through the xy plane. Okay. The xy plane is the plane z equals 0. So it needs to be z equals, so we're starting at z equals 0. Okay. And it exits through the edge of the paraboloid, right? The paraboloid is z equals 1 plus x squared plus y squared. So 1 plus x squared plus y squared. Z equals 1 plus x squared plus y squared. Okay, so this is the right idea, but it's not quite right yet. My limits of integration are involving our rectangular variables, but I'm only integrating with respect to z, and then my polar variables are in theta. I need to get rid of the x and y. I need to rewrite this equation, z equals 1 plus x squared plus y squared, in terms of the polar variables. Okay? So this, the paraboloid up here, z equals 1 plus x squared plus y squared. I rewrite it in terms of the polar variables. Now z stays the same, z equals z. But x squared plus y squared is r squared. Now that equation is in terms of my cylindrical variables. Okay? Just involves r, theta, and z. So z equals 1 plus r squared. All right? So it's not enough for the integrand to be in terms of those cylindrical variables. The limits of integration also have to be as well. All right? Now, the first step here, we integrated with respect to r, and just like normally integrating a triple integral with respect to rectangular variables, z is both a cylindrical variable and a rectangular variable. So it does the same thing as it did before. It collapses that dimension. Okay? So I'm going to have something in the xy plane. And if we were to look at this from above, we wouldn't be able to see the paraboloid at all, really, right? So imagine looking at this from above, what would we get? We'd be left with a circle equal with the radius equal to the edge of the cylinder. Okay, so a circle equal to the radius of the edge of the cylinder. So the cylinder was x squared plus y squared equals 5. So let's convert that to cylindrical coordinates. That'd be r squared equals 5, or r equals the square root of 5. Okay. And just so you could see it a little bit better done, that was their shape. But if we look at it straight down the z-axis, because that's what we integrated, that's what we are left with. We collapse it in the z direction. And so we're only left with integrating these two variables now, x and y, over this two-dimensional region, a circle of radius equal to the square root of 5. Okay? Now how do I slice it up? Well, if I was still in rectangular variables, I'd have to slice it up this way. Or this way. Right? And that doesn't seem like a whole lot of fun because no matter what I do, the edges would be circles. Circles, when we integrate circles, if we express the edges of circles in terms of x and y, we'd end up with square roots. Integrating square roots isn't fun. Okay? But fortunately, we have converted to cylindrical coordinates. And now that we're done with the z, the two dimensions we have left, we're integrating with respect to r and theta, our polar variables. So we're going to integrate the rest of this just like we did in the previous section when we dealt with polar coordinates. Okay? So I'm going to slice it with respect to the radius. So I'm slicing it out from the center. Now, each one of those slices, it starts at the origin where r is equal to 0, and it ends at the edge of the circle. This circle has radius equal to the square root of 5, so it ends at r equals root 5. Okay? And finally, theta. For theta, I look at the angles of these slices, and these slices go all the way around. So my theta will go from 0 to 2 pi. Okay? And I'm not actually going to evaluate the integral. The evaluation is pretty straightforward. But that is the setup. And that's the hardest part for these multivariable integrals, setting up the limits of integration. For this example, we want to find the volume of the solid bounded below by the plane z equals 1 and above by the sphere x squared plus y squared plus z squared equals 2. So first question, how do we find the volume? Okay, now this is in a section that we're dealing with triple integrals. Usually finding volume is a double integral thing, right? We find the volume underneath a function, but over a certain region in the xy plane, right? But we did learn also that we could use double integrals to find area. So recall that if I look at the double integral over some region R and I'm integrating just function 1 over that area, that gives me the area of region R. Okay. Now, in actuality, we are calculating a volume, but the cylindrical shape has this as a base and only height 1. And so you calculate the area of the base and then multiply by the height of this function to get your total volume. Because the height is 1, it'll just stay the same as the area, right? Well, we have a similar situation here that we can use a triple integral to find the volume of something. So if I want the triple integral over some volume E, some three-dimensional region E, if I integrate just the function equal to 1 over that volume, it will give me the volume of E. Okay, so that's going to be what we use to calculate this. All right, we're just going to do a triple integral over the function equal to 1. All right, so let's start by graphing our region. Okay. So we have two things. We have a volume. It's bounded below by the plane z equals 1. Okay, so z equals 1. Let's put it right here. Z equals 1. So we have a plane that goes through that. Okay. And it's bounded above by the sphere x squared plus y squared plus z squared equals 2 squared. So that's a sphere of radius 2. Okay, so we have this radius here, or this sphere here, and they intersect right at 1. Okay, so let me do it from one side. There we go. And so this volume up here is what we want. Okay, let me show you that in the 3D calculator so you can get a better sense of what we're dealing with. So we have the plane z equals 1, and then we have this sphere. And we want the region, that little part of the sphere that's cut off by the plane, so that the region is bounded below by the plane and above by the sphere. So we get this. That we want the volume of this region. Okay? All right. And again, I like to draw it one more time just so I could get a little bit clearer of a picture of what we're dealing with. Okay, so I don't have to be exact here. Just a rough sketch of what we got. Okay. So we want to take the triple integral of this region. Did it name the region? It did not. So let's call this region, let's call it E. Okay. So we're going to find the triple integral of this region, E. And because we want the volume, we're going to integrate it over 1. Right? Now, we're practicing cylindrical coordinates. So let's go ahead and use cylindrical coordinates for this problem. It's not an obvious problem for cylindrical coordinates, right? Because there's no cylinders involved. And we don't have any x squareds plus y squareds in the integrand. That's usually a dead giveaway, that cylindrical coordinates might be a good option if you see x squared plus y squared, because then we could swap it out with r squared, right? But it's actually still a pretty good problem just because I could separate it into what's going on in z, and then once I collapse the z, I'll be left with a circle. And looking at this from above, once I get rid of that z, that would be real good to use polar coordinates on that, right? Okay, so let's set this up. So my function is 1, but I'm going to convert to cylindrical coordinates. And since the x and y get converted to polar variables, that means I need an extra factor of r. So I need 1r. Okay, so let's integrate first with respect to z. We can see if we kind of consider the strands going through this. That I'm going in through this bottom surface, through the plane z equals 1. And out through the top surface, which would be the surface of the sphere, right? So I need a way to write the sphere as z equals something. Right now we have the sphere as x squared plus y squared plus z squared equals 2 squared, or x squared plus y squared plus z squared equals 4. But I need it to be written as z equals something. So I'm going to solve for z in this equation. So subtract x squared and y squared. Okay, take the square root. I get plus or minus root 4 minus x squared minus y squared. Now that gives me two options, a positive and a negative. I'm in the upper half of the sphere where z is positive, right? So I want the positive root. Now I do have to do one more thing before I plug in. I'm still using my rectangular variables. I need to swap them for cylindrical variables, okay? Notice if I factor out the negative, this this expression under the square root becomes 4 minus x squared plus y squared. We get that x squared plus y squared that I said was so important. We can rewrite that as r squared. Okay, so I'm going to take the top half of the sphere, so the positive root, and I'm going to rewrite x squared plus y squared as r squared. So I can express that top surface as z equals square root of 4 minus r squared. Okay? And z is done, which means I can collapse that dimension. So if I collapse that dimension, look at it from above, I'm going to have a circle, right? I'm not quite sure what the radius of the circle is yet, but I know it's a circle. Okay? To find the radius of the circle, the edge here, I look down from above, this would be the edge of the circle right here, right? And that's going to be where the plane, this plane, intersected with the sphere. So that's where I want it, right? If I go back here, the edge of the circle is where this plane and the sphere intersected. Okay? So let's find the intersection of the plane and sphere. C equals 1, and x squared plus y squared plus z squared equals, what was it, 4? Yeah. Okay, so I'm just going to plug the one into the other. I get x squared plus y squared plus z squared equals, plus 1 squared, plugging that 1 in. Plus 1 squared equals 4. Subtract the 1, x squared plus y squared equals 3. Let's convert it to our polar coordinates, our cylindrical coordinates. X squared plus y squared becomes r squared, which means r is going to be equal to the square root of 3. Okay? So this edge here, the radius of this circle is r equals root 3. Okay, so if I slice it up, holding theta fixed and letting the radius change, so I'm going from center out, then I could say I could see the beginning of each slice is going to be at the origin, so r equals 0, and the edge of each slice is going to be at the boundary of the circle, which, since the circle is radius root 3, I go to r equals square root of 3. Okay? And again, in this case, I want the whole circle, so I'm going to go all the way around. So theta goes from 0 to 2 pi. Okay. Again, I'm not going to actually evaluate this, but that is how you would set this up. So much for cylindrical coordinates. Let's now look at doing triple integrals with spherical coordinates. Spherical coordinates are going to be a little bit more unfamiliar. With cylindrical coordinates, we were really just applying what we already knew about polar coordinates and applying that to 2 of the 3 variables, right? But spherical coordinates, we're really changing all 3 variables. Okay, so first let's just review the relationships between our spherical variables and our rectangular variables. If you haven't memorized these yet, nice time to do so. Okay, x equals rho sine phi cosine theta. Y equals rho sine phi sine theta. Z equals rho cosine phi. rho squared equals x squared plus y squared plus z squared. Tangent of theta equals y over x. And phi is equal to the arc cosine of z over square root of x squared plus y squared plus z squared. Okay. And then we do sometimes find use for one other equation. I call it the bonus equation. Rho sine phi plays the same role as r does in cylindrical variables. So if you have x squared plus y squared, you could replace it with rho sine phi all squared. Okay. Just as in with cylindrical coordinates, if we are going to change to spherical coordinates, we need to make an adjustment. So if we're evaluating some triple integral over some region E, and we're integrating some function f of x, y, z with respect to those three variables, if I'm going to change the coordinate system to my spherical variables, rho, theta, phi, okay? Then, oh, I didn't leave enough room there. Then just as we got an r before when we converted to cylindrical coordinates, we get an extra factor here also to make the adjustments. Rho squared sine phi. So anytime you convert to spherical variables, make sure you throw in an extra rho squared sine phi. Okay. I'm not going to derive for you today where that comes from. I believe your textbook has a short derivation. The idea is the same as when dealing with where that extra r came from when converting to the polar coordinates and with a double integral, or with to cylindrical coordinates and with the triple integral. Okay. And we will learn more generally how to find these, how we need to adjust for the transition when we make changes of variables within just a couple sections. Okay, so we'll find a more general way to find this pretty soon. For now, just know that it's there. Whenever we convert to spherical variables, we need to include this extra factor. All right. Also, whenever integrating with respect to spherical variables, we almost always go in this order. Theoretically, you could go in any order you want, okay? But your life is going to be easier if you go in this order. So first, integrate with respect to rho, then with respect to theta, then with respect to phi, okay? Obviously, spherical variables, like all the other coordinate systems we've learned about, they're not going to be useful in every situation. But in the right situation, situations that have a geometry that is inherently spherical, it will greatly make our lives easier to convert to spherical variables. Okay? Let's take a look at this example here. We want to evaluate a triple integral over a volume E, where E lies between two spheres. The sphere of radius 1 and the sphere of radius 4. Okay, so easy enough to draw, maybe a little hard to visualize. Okay, so I have a sphere of radius 1, 4. Okay. Sphere of radius 1. And That's the inner boundary. And the outer boundary is going to be a sphere of radius 4. Okay, so you kind of have this shell, right? This hollow shell. It's this thick shell, but it's got a hollow center. Okay, that's what we want to integrate. Now, this is an excellent example of a problem that is ideal for spherical variables because I'm integrating between two spheres, right? If I tried to do this in rectangular variables, I'd have to split this into several pieces to make it work. Okay? It's not a good problem for cylindrical variables either, but for spherical variables, it's perfect. All right? So what we want to do, we're going to take our triple integral here over E, 1 over x squared plus y squared plus z squared. And let's rewrite it as a triple integral over spherical coordinates. Okay, so that means my integrand, I'm going to need to rewrite it in terms of spherical variables. Fortunately, that's pretty straightforward, right? X squared plus y squared plus z squared is just my radius squared, rho squared. So 1 over rho squared. So that it makes my integrand nicer, which is good. But because I'm converting to spherical coordinates, I need to add that conversion factor. Rho squared sine phi. Okay? Integrate with respect to rho, then theta, then phi. We almost always use this order of integration. Okay? So let's find our limits of integration. So we're integrating first with respect to rho. If we fix theta and phi and just let rho change, that means we'd be shooting out from the center and just let our radius change along a straight line going outward. Okay, so we could, depending on how we fix rho, theta and phi, we could be pointing in any direction. Okay, but we're going to shoot out from the center, starting at rho equals 0, out from the center. We actually enter the volume when we hit the edge of this inner sphere. We want to count everything between the two spheres, and then we exit the volume when we hit the edge of the outer sphere. Okay? And that's going to be the same no matter where we draw that that strand through the volume. Okay? So rho, we want to start counting rho when it gets to 1, the inner sphere, right? This guy right here is the same as rho equals 1 in spherical coordinates. And then I want to count it all the way until I get to the edge of the outer sphere, which would be rho equals 4, which is the equation of this outer sphere. X squared plus y squared plus z squared equals 16 is rho squared equals 16, or rho equals 4. Okay? And now we need to think about theta and phi. Now theta is our polar variable, our polar angle. And we would start here, and we want to go all the way around this, don't we? We want to go all the way around this sphere. And so it would go from 0 to 2 pi, the full range of theta. And then our azimuthal angle, phi, we want to start up here, and we want to hit everything. We want to go all the way around the edge of the sphere here. We want to count everything all the way down from pole to pole, from the North Pole to the South Pole, right? So that would be 0 to pi. Remember, theta can range from 0 to 2 pi, but phi generally ranges only from 0 to pi. Okay, so that's a setup. You'll notice that the rho squareds will cancel. And so we only have to integrate sine phi, which is nice. And the limits of integration are all just numbers, which is also very nice. Okay? Again, I'm not going to evaluate it for you, but you've got the setup. To finish us off on this section, I wanted to take another look at this problem. Now, we've already set up this problem using cylindrical variables, but it actually feels like it'd be more natural in spherical variables, right? So let's give that a try. So just as a reminder, this is the problem where we have the plane and the sphere, and we want the region bounded above the plane and below the sphere. So this region right here, okay? And since it's actually a portion of a sphere, spherical variables seem like a good fit, right? So let's take a look. So let me just draw the region we're integrating over here, just for reference. So here's radius 1, 2, okay. So this is the volume we're integrating over. We want to find the volume of this region. Okay, so remember that's going to be a triple integral of this guy over the function 1. Now, since we're going to convert to spherical coordinates, that means we take that 1 and we multiply it by the integrating factor that we get from the variable conversion, which for spherical variables is rho squared sine phi. And let's integrate with respect to rho, then with respect to theta, then with respect to phi. All right. Now, the first two variables are going to be pretty straightforward. So if we integrate with respect to rho, we would be looking at these strands that come from the origin through the bottom and then out through the sphere. Okay? So no matter where I draw it, coming from the origin, the first thing I would hit would be the bottom surface here. Now that's a surface z equals 1. Okay? But I need to express it in terms of rho. Okay? So I need to re-express z equals 1 in terms of rho. So z equals 1. What I'm going to do is I'm just going to replace z with what it is in spherical coordinates. Spherical coordinates, z is the same as rho cosine phi. Okay? So if I want to isolate the rho, I just divide both sides by cosine phi. I get rho equals 1 divided by cosine phi, or rho equals secant of phi. So that's going to be my bottom limit of integration. When rho is equal to secant phi, that's when we hit that bottom plane. Okay? Now what about the top plane? I'm sorry, not the top plane, the top surface. The portion of the sphere. Okay? Well, the sphere is the sphere x squared plus y squared plus z squared equals 2 squared. So x squared plus y squared plus z squared equals 4. Which means rho squared equals 4, since rho squared is equal to x squared plus y squared plus z squared. If I take the square root, I get rho equals 2. Okay? Makes sense. It's a sphere of radius 2. And so rho is the spherical radius, and so it should hit the edge of the sphere, radius 2. Okay? So that's where, for every strand that hits that that volume, starting at the origin, going outward, holding theta and phi fixed, but letting the rho change. It's going to start by hitting the edge of this plane, rho equals secant phi, and then exit through the sphere, which can be described by rho equals 2. Okay. Now for theta again, I want to go all the way around. Right? It's symmetrical in this direction. I want to go all the way around. So theta is going to be from 0 to 2 pi. Phi, though, phi is going to be a little trickier. Okay? Let me erase these so we have room to really express what's going on with phi. Maybe I'll just erase the 1. Nope, I'll erase both. Okay, so for phi, what's going to happen is I want just the angle from here to here. That's the region that I want, right? That's the region that I want to count. If I go any further, I go, say, from here to here, then I'd be counting the sphere all the way down there. That's not what I want. I want just the angle from here to here, and then theta takes it around. Theta goes all the way from 0 to 2 pi, so it will go all the way around the edge. I just need to make sure I stay within the range. So I need to know the angle from here to here. That's where I'm counting. Okay, now this angle up here, that's phi equals 0, right? Phi starts on the positive z-axis. What I need to find is this angle here. Okay, so how do I find that? Well, I know that, just as a reminder, z equals rho cosine phi. So cosine of phi is equal to z over rho. Now the z at this point is 1, right? Because I'm in this plane. So z is equal to 1. But I'm also at the edge of the sphere. And this sphere has a radius of 2. So rho is 2. Okay? And so I want my phi to be the arc cosine of 1 over 2. All right? So draw a little triangle there. Or you know what? That could just be my answer. Arc cosine of 1 over 2. Okay? The integral set up. And we just need to evaluate it for our final answer.